All right, today we will start a new discussion. It's also about reconstruction or the improvement of signals, particularly images. And it's going to be, let me open a new page. It's going to be from a perspective where we are merging some information, some side information, to improve the content or the fidelity of the information, which makes the signal or the image. Because imaging systems are sometimes not very much capable of depicting the details or the whole information. Sometimes it's not possible because of the limits of our optical system, for example. That's usually valid for astronomical imaging. That's a good example because things are very much far away and our optical aperture sizes are limited by humans. So it's not really possible to have very sharp images. You could go there in space and take the picture, but they are just galaxies far away. Or another thing that you can do instead of making a huge single lens is to take pictures from here and there and try to combine all the information, for instance. That kind of a combination, one technique that can be used for combining the information is known as reconstruction from projections or alternating projections. Let me put it that way. So, alternating projections. Here, the term projections correspond to making an information-wise projection onto a set. That this is an optimization methodology. It's also very well known by, let's say, industrial engineers, for example. It looks like this. You have a few sets, let's say 2 sets, that has an intersection point which corresponds to your solution. So you're trying to optimize that intersection point. So what you do is you start from one point out of out of these sets. It does not belong to either of the sets. It may belong to the set, but the thing that you have to do is you must make a projection to its boundary, which is an orthogonal projection. So these sets must be convex. Okay. Otherwise, you cannot really define a single orthogonal projection. So you arrive at a new point, and then from that point, you make a projection to the other set. And then from that point, you make a projection to the other set, to the boundaries, of course. And when you zoom there, it converges to the intersection point if there is a solution. That's a solution finding idea. But this idea has been used or utilized in image reconstruction too. Sometimes it's even used for image formation. I will come back to this convex projections and we will discuss a little bit further about some other applications, some other utilization problems as well. But image formation, for the time being, will be an excellent example to start with, because it will be forming the image from not the image. Okay, so we don't even have a single image to start with. So it's not like the astronomical imaging, because over there, no matter how blurry or how inappropriate it may be, you may still take photographs of the deep space. But sometimes it's not possible to even take the photograph. The only thing that you may encounter will be some side information. How can we merge all those side informations, like the thing that I'm describing here? We will start with the analytical solution first, without any optimization using alternating projections. But so we will start with the analytical and image processing way of doing things, signal processing way of doing things. And then I will show you a methodology to use alternating projections. And this image formation example is a reconstruction from projections. Which will lead to an imaging technology. So it's not taking a photo or anything, but it's an imaging still, that which is known as the computed tomography, CT. And here, the term projection does not really correspond to the alternating projection way of projecting your information onto a convex set or something like that. It's not that one. This one is really the projection signaling or imaging in computed tomography. I will explain that. So what is computed tomography doing? First of all, let's remember that one. It is taking the image or it is trying to grab the image of a slice of your body, slice. So it's impossible to take that photo, right? You cannot really cut the person and look at what's going on inside. And there's no other way, if you think carefully, well, how can you take a picture of a slice of your body? So what you really do is you take several pictures, but very thin, slice-wise pictures of your body at different angles, from different angles. So let's assume that, for instance, this is the slice of your body. It is quite unbalanced and asymmetric, unfortunately, because I have drawn it that way. Of course, we don't really encounter such tissues or such profiles in our body, but I'm just making some random images. So inside it, for instance, the tissue inside this region is light, but in the shaded region that I have drawn, there is some extra tissue, an organ. And here maybe another one, which is even denser, maybe a bone is passing from there. So this slice is what you are trying to visualize. One projection, one signal capturing projection is done as follows. We have an axis, and from here, along this direction, we are taking an X-ray image. But the X-ray image along this direction is very thin. So the image that we will come up with will be like 1 pixel by 1000 pixels or something like that. It may be thicker than that, of course. It can't be just 1 pixel wide, if you think. But this is like the image that we get. It's a narrow one. And we are not interested in the variation along the vertical direction, but we are interested in the horizontal direction, because that is the slice that we are trying to image. And when we take this kind of an X-ray, I will assume that the signal that I get is essentially one-dimensional, and that one-dimensional image is consisting of an accumulation, a summation of the densities of the tissue. In normal X-ray imaging, it's actually the negative, of course, because the more dense tissues the X-ray passes from, the more it gets attenuated. It shrinks in the value. It has less value. So we negate that, and we assume that it's actually summing up all the densities of the tissue. So maybe the image will look like this. Okay. It doesn't really look like a good drawing at, I have erased in it everything. I'm just so sorry about that. The eraser just erased everything, sorry. But this is the profile that I get. Why did I draw it like this? Because as you see around these places, it really corresponds to this part. Okay, it's a denser part, an issue, liver maybe, I don't know. And therefore, its accumulation, its summation is showing some larger signal value, right? And here we see the problem from this. It's not a problem, but we are like accumulating that dense image. Let's assume that it's a bone, therefore its density is way more than regular meat substance. So it shows, of course, I'm assuming that coordinate-wise, it corresponds to that region. It may be inaccurate, unfortunately, according to my drawing, but I think you understand the point here. So this signal is one signal that we have, which I will denote as this signal. I will notate as g theta of s. So this is the s axis. Okay, so the axis I will assume to be an s axis. It's not the Laplace s I'm talking about here. It's just the axis name that I'm giving along a certain direction, and theta is essentially this angle. Okay, it makes that much angle from horizontal, and as you see, if you change that angle, it will generate different g theta of s signals. All right, so I will have many of those one-dimensional signals, regularly or gradually increasing theta, rotating all the way back. I will take a lot of one-dimensional signals, which will all look like something like this. Okay, and from these signals, from these one-dimensional signals or information, is it really possible to reconstruct or to reimagine the image corresponding to the slice which is shown here, this one? Can we really reconstruct that information up to a resolution, of course? This g theta of s is, as you see, it's a one-dimensional signal, and it has its one-dimensional Fourier transform, which may be written as g sub theta of omega. So s is the space domain, and omega is the frequency domain notation that we have. Now, what is g theta of s if you consider that this two-dimensional signal is essentially f of x and y? Okay, that's what we are trying to reconstruct. With respect to f of x and y, g theta of s can be written as g theta of s is it's a transform. It's called the Radon transform. So I'm going to represent it with the calligraphic R. It's the Radon transform of f of xy, which is equal to a directional integration of f of xy, because we are integrating, but the integration must be done after multiplying with line integral, lines, two-dimensional line formulas. And the two-dimensional line formula corresponding to this angle for a certain s is this, delta of x cosine theta plus y sine theta minus s. okay, dx dy. It's all from minus infinity to plus infinity. Theoretically, we don't need the limits here. We are limited or bounded by the bounds of f of x and y. First, you must convince yourselves that this actually is a line at theta degrees, or angle theta at theta tilt and shift s. Okay, this is the formula of that angle. Now, knowing this, when you multiply an image with a line, with a line impulse, what you will get after the multiplication is only the scaled line impulse, and the line impulse will be like, I will try to illustrate something here. It will be like this. Okay, it's a very thin slice. It will become this line integral. Previously, it was a razor sharp, very thin slice with uniform magnitude of 1. But now, after multiplying them with f of x and y, it becomes those valued slices. So this valued slice, I integrate. I find the area underneath, and that area will give me, for example, the value of g sub theta of s at this point, at this certain point corresponding to the certain s value. Okay, that's what g theta of s is, and that's what a Redon transform does. Now, interestingly, this is the fascinating analytical way of doing things. The relation between g theta of s and f of xy is complicated, like this one. It's multiplication with a line impulse and integration, etc. But the relation between, let me first denote it. This f of x and y will have a Fourier transform, which is capital F of omega 1, omega 2. The relation between g theta of s and f of xy is complicated, but the relation between f of omega 1, omega 2 and g theta of omega is not that complicated. In fact, it is so simple that they are the same. They really correspond to the same thing. And the way to see it is the following. They correspond to the same thing, but they have different notations. One of them is g sub theta of omega. The other one is f of omega 1, omega 2. So how can we relate those two entities? For that, we have to write f of omega 1, omega 2 in the format of f of omega cosine theta, omega sine theta. This is a polar coordinate way of writing things. And when you write it like this, and with the incorporation of this impulse here, saying delta x cosine theta plus y sine theta minus s, indicates that s is essentially x cosine theta plus y sine theta. So the rest is actually trigonometric derivations, which will tell me that x is s cosine theta, sorry, let me remove s times cosine theta minus u times sine theta. Here I am inventing a new terminology or a new notation, which is u, but you can think of it as the orthogonal direction of S, okay? That's S is like this, and therefore U is the orthogonal to that. We will not be using it anyway, but we are just notating it. And Y is equal to S times sine theta plus U times cosine theta, which makes us this, or gives us this new formula. By the way, S is equal to x cosine theta plus y sine theta, but I have incorporated a new notation, which is actually telling me that I need u as well, which is minus x sine theta plus y cosine theta. It's just solution of the system of equations. G theta of S is equal to, now I will rewrite the double integral at the top right corner from f of x and y, but I will write x and y in terms of s and u. And if I do it that way, then the integration will be along only one direction, which is this s direction, along the s direction. So it will be a single integral now, from minus infinity to infinity, but it's still bounded by the support of f. F of x, which was s cosine theta minus u sine theta, sine s times sine theta plus u cosine theta, and oh no, this is not s, excuse me, I have made a mistake. So this actually is not the s direction, it's the u direction. S is the direction which is orthogonal to that. Okay, this direction was s. So I have to put a du here. Now, as you see, if you focus to this last integral that I have written, it's in terms of the inside. F is in terms of several things. One of them is S, okay? The other one is U, and the other one is theta. And then I am integrating with respect to U. So U is gone at the result of this integration. U goes away, and we are left with only S and theta. That's why g theta of S is in terms of S and theta. And as if this equation is not complicated enough, now I will take the Fourier transform of it. And the Fourier transform will give me g theta of omega. It will be a one-dimensional Fourier transform because it's a one-dimensional signal, g theta of S, as you see. And it will become an integration due to the Fourier transform and the integration which we already had here, one line above it, and f of s times cosine theta. I have to repeat it once again. U times sine theta and s times sine theta plus u times cosine theta, and e to the minus j omega s. That this is the Fourier transform. du was the previous integration increment, and ds is now the new the new integration increment. Okay, now I will roll back from this equation to the xy equation, and that's going to be a little bit tricky. First we have to consider we know the relation between xy and us. Okay, that relation we have already discovered. They are here. Okay, these formulas are already relating s and u to x and y, but du times ds is something that we have to think a little bit more carefully, because we don't know the relation between their increments. But as we can see, u and s are, it's actually just a rotated framework with respect to x and y. Look at the u and s, they are orthogonal to one another, and it actually corresponds to a rotated version of x and y. Therefore, dx times dy magnitude and du times ds magnitude are the same. Okay, they are just plain normal rotations. So they don't interrupt the magnitudes. So, we can say that this is equal to dx dy. So when I change all u and s into x and y, when I change back, I will be safely putting dx and dy at the right-hand side of the double integral, and I will do that now. And I'm going to see that this is x. It was x anyway, all along, and this was y. The only thing that I have to take into account is I have to substitute s is equal to x cosine theta plus y sine theta. Okay, that substitution is what I need to write. So I will say f x and y and e to the minus j omega in parentheses x cosine theta plus y sine theta. You may be curious about why I'm writing these. Why are we doing this? I will explain later. Because I have to prove the argument that I have said in the beginning. I said that this, the two-dimensional Fourier transform of my image, and the one-dimensional Fourier transform of the radon transform, theta of omega, are the same, I said. That's what I'm trying to prove. It needs a proof. And when you write it like this, you see that this is equal to again the double integral fx y e to the, I will write it in this form, minus j it's showing a jitter, sorry about this, e to the j x times omega, the pen is acting erroneously, x times omega cosine theta, and let me put it in a parenthesis of j plus y times omega sine theta dx dy. Okay, and from here I see that this and this obey the rule of the Fourier transform. If you say that this is omega 1 and this is omega 2, it is like e to the minus j x omega 1 plus y omega 2 dx dy, which is the Fourier transform of f of xy. So the whole thing, therefore, boils down to the Fourier transform of f of omega 1, omega 2 at omega 1 being omega cosine theta and omega 2 being omega sine theta. So I can write it like f of omega cosine theta comma omega sine theta. Now, remember this. Let's put it in a box, in a green box. remember this formula, and let's go back, roll back, and look at this formula, which was the polar coordinate wise expression of f of omega 1, omega 2. So what was f of omega 1, omega 2? It was the Fourier transform of f of xy. And meanwhile, I took the Fourier transform of g theta of s and obtained g theta of omega. You see that g theta of omega is also equal to this. So, it's giving me an impression that the Radon transforms Fourier transform and the images Fourier transform are the same things. Since we have only the Radon transform, but we don't have the image, let us solve this problem by finding the Fourier transform of our observations first at various theta angles, and then it will give me the Fourier transform of my image. So I will first form it, construct it. I will construct f of omega 1, omega 2, and I will take the inverse Fourier transform of it, which will give me f of x and y. How can I do that? Technically, the way to do it is like this. Let me roll back. For example, at theta is equal to 0 degrees, I take a slice. I say that it's equal to g theta of s, which is, let's say, g0 of s, okay, 0 degrees. And then I take its Fourier transform, g0 of omega, and this is the omega axis, and I put it on it, put the Fourier transform values on this line. And then I take another angle, and I say that omega is that direction. So it's, let's say, g1 of s, and I take its Fourier transform, which is capital G1 of omega, and then I paint it here. And at another angle, I paint it here. Okay, these are all complex valued Fourier transforms that I'm painting. At all angles, of course. Clearly, we cannot have all of the angles because ideally, I must be incrementing theta just gradually, continuously change it, but it's not possible, of course, because we have computers. Therefore, we just increment by some delta theta, some angles. So the situation becomes like this. Now, as you see, this becomes like a Fourier image. You render, you paint an image. One by one, patch every location of this two-dimensional Fourier space. Once you have that Fourier image, you call it to be f of omega 1, omega 2, and then you take the inverse Fourier transform of it, and you get f of x, y. Now, is that clear? Did you understand what we did? We start from this g theta of s, the one-dimensional signal for a certain theta, and then we take the Fourier transform of it, and then we painted that Fourier transform along that direction. Then we increase theta a little bit more. We take a different g theta of s. We make a different measurement. Of course, we need extra X-rays every time we do a change in the rotation angle. We have to take the image again and again. We have to take the X-rays again and again at all these angles. So we have to generate several GT2 of S for several theta values. Then one by one, we take their one-dimensional Fourier transforms, and then we paint them into the two-dimensional axis. And we make a two-dimensional Fourier shape. Finally, we take the inverse Fourier transform of that, which will correspond to f of x and y. So this is the way computed tomography works, and it still works this way. But in the intermediate stages of calculations, the computer power was not sufficient to do all of these things. And it requires several Fourier transforms, huge inverse Fourier transforms. It requires a lot of memory. So it's problematic, as you see. But nevertheless, at least theoretically, it's possible to do it if you have a strong computer. And that necessity of a strong computer is one of the reasons why such instruments, such medical imaging instruments, are terribly expensive. And it also gives us an idea about why the name of this tomography imaging is known or is named as computed, because there is a computation. Unfortunately, I wouldn't say unfortunately, but for the analytical way of doing things, this tomography has its drawbacks. It has several drawbacks. First of all, I would like to avoid having a computed tomography imaging for myself when I go to a hospital, because it requires several X-ray images from several directions, okay, by one. So it's exposition to X-ray radiation multiples of times. So it's not very good. So you should avoid it as much as possible, as long as you can. But it's critical, of course, you have to consult to that, because observing something inside may be critical, of course. And that's one drawback. And magnetic resonance, which is a completely different technology, utilizing only magnetic resonance, as the name suggests, and grabbing the information from the resonant points. It does not require X-rays, therefore it's safer to do it. But for the current situation, as far as I know, the precision or the resolution, the imaging resolution of computed tomography is still better than magnetic resonance, because you can just reduce the number of reduce the angle increments by increasing the number of X-rays that you grab. You can make it very high resolution. But still, now comes another problematic issue of the computed tomography. As you see, the frequency accuracy is better at lower frequencies because of that intersection. That corresponds to zero frequency. And as you radiate from zero frequency onwards, it means you are increasing the frequency. But for lower frequencies, the frequency resolution, frequency accuracy will give you a good layout of the image. But at higher frequencies, around here, for example, the separation between two rays may get wider and wider and wider. So the accuracy of the frequency, the resolution of the frequency, in other words, is not as good at higher frequency ranges. You can just incorporate some new measurements, if you wish, to improve the frequency accuracy, but it means taking more X-ray images. So this is the analytical way of solving the computed tomography or computing the tomography. There are some improvements to this one. I will also indicate or explain some of the improvements to this one, but this is the general idea. So, okay, this is the idea, the overall idea. Now, how can we increase the efficiency in terms of computational power, at least? What we can do, for instance, is by taking the inverse Fourier transform expression, this one, into account and seeing what is really happening overall in time domain. Because I switched to Fourier transform in 1D and switched back to time domain by taking the inverse Fourier transform. But could everything be done in time domain? And the answer is a clear yes. So let's see what's happening in time domain. So I'm taking the two-dimensional Fourier transform of capital F omega 1, omega 2. So I'm writing down the formula, capital F omega to the J omega 1x plus omega 2. Why am I capital omega? Sorry. I'm more stuck with this capital omega notation because this is the continuous time Fourier transform and inverse Fourier transform. But we can also write it like this anyway. Plus omega 2y d omega 1 d omega 2. Now I will switch the notation of omega 1, omega 2 into omega and theta. So f of x and y will be equal to, I will try to write everything in polar coordinates, in other words, 1 over 4 pi square. This first integral will be tracing from 0 degrees to 180 degrees. So it's actually from 0 to pi in radians, of course. And the other one, for omega, omega is ranging from minus infinity to infinity. Okay. And inside it, I will have f of omega cosine theta. So I'm switching back to the theta and omega notation. Cosine theta, omega sine theta, e to the j, let me put omega 2 here, j omega x cosine theta plus y sine theta. Now I want to put d omega d theta here, but before or the left d omega d theta, I must put the so-called Jacobian of the integration or the parameter change. And that Jacobian is absolute value of omega. So the relation between d omega 1, d omega 2, and d omega d theta is together with the magnitude of omega. That Jacobian you may remember from calculus. And I really shouldn't go into the details of that because it's it would be just a revisiting of advanced calculus. For those of you in the graduate level who haven't taken the advanced calculus, you should better do that. Now, with this knowledge, I will continue. I will write it like 1 over 2 pi. I'm splitting 1 over 4 pi square into two components. And this first part is from 0 to pi. And then I will put another 1 over 2 pi. And the second integration from minus infinity to infinity. And inside it, what am I going to write? First of all, this thing here is equal to g theta of omega. Okay, I'm going to write it that way. Excuse me. G theta of omega. And then I will put the absolute value of omega here, and e to the j omega x cosine theta plus y sine theta d omega d theta. Now, I want you to focus to this part. As you see in the frequency domain, there seems to be a multiplication. So I'm multiplying g theta of omega and the absolute value of omega in the frequency domain. If I multiply in the frequency domain, the corresponding inverse Fourier transform of that, which is the red curly bracketed place, that is the inverse Fourier transform. By that inversion, it will correspond to convolution of two signals. One of them is the inverse Fourier transform of g theta of omega, which is g theta of s. The other one is the inverse Fourier transform of absolute value of omega. Those two must be convolved. So let's write it that way. But I will start from the, excuse me, from the green part, which was g theta of omega times absolute value of omega. What is the inverse Fourier transform of it? So if this is the Fourier transform, what's the inverse Fourier transform of it? It's the inverse Fourier transform of g theta of omega convolution with inverse Fourier transform of absolute value of omega. Okay, that is convolution versus multiplication in Fourier domain. The thing that we need to know is not this one, because this one is clearly g theta of s. It's just the time signal. How about the absolute value of omega? If there is only omega, it would look better, because or even better than that, if there is j omega, when you multiply some Fourier transform by j omega, it actually corresponds to a derivative operation in time domain. You remember that? So absolute value of omega is somehow related to the derivative, but it's essentially something like this. It's like this thing is equal to j omega times minus j times signum or sine of omega. Okay. And this j omega here corresponds to d by dt. And this part, minus j times signum, corresponds to the Fourier transform of 1 over t. So if you take the Fourier transform of 1 over t, you will get minus signum omega. And j omega's inverse Fourier transform is d by dt operator. So this convolution, how are we gonna make the convolution of that? It looks bad actually. The overall thing seems to be g theta of s convolution with d by dt of 1 over t. Should we really, I mean, the operator d by dt is a linear operator, so is a convolution. So I should actually take the derivative of g theta. By the way, I'm making a mistake here by writing it in terms of t, but actually t is the s parameter here. So it's essentially more like this, g theta of s convolution d by ds 1 over s. More like this one. And what is it equal to? It's equal to I think it's better to take the derivative of g theta of s convolution with 1 over s. Since both the derivative and convolution are linear operators, they can be interchanged, okay, in their orders. And the convolution could be written as d by ds. The convolution is an integral from minus infinity to infinity g theta of tau. Tau is the tau of t, but this is the tau of s, actually, over s minus tau. That is like t minus tau, theta. This is the convolution formula. If I convolve of s and 1 over s, the integral part is what I will get, and then I will take the time derivative of that. And I will give a name to this one because it looks bad. But actually, it's just taking the derivative of a filtering operation. There is a filter whose impulse response is like 1 over s, or h of t is 1 over t. So I'm convolving my g theta of s signal with that 1 over s first, perform that filtering, and then I take the time derivative of that. And I can call the result r theta of s. It's just the name that I give. If I put that r theta of s back into the equation of what is fx and y, it's equal to 1 over 2 pi, the larger integral outside, from 0 to pi, r theta of s d theta. Okay. And that is 1 over 2 pi from 0 to pi. I'm just going to write it in an explicit form. Instead of s, I'm going to say x cosine theta plus y theta, because I need to have the output, the result, in terms of x and y, d theta. This the right-hand side, basically, this part is known as the radon's inversion formula. Of course, inside it, you need r theta, but r theta is not a difficult thing, and it can be processed in memory efficiently for each one-dimensional signal. For each g theta of s, you can very quickly calculate r theta of s, and once you have those r theta of s's for all theta, you can use this radon's inversion formula to roll back all these r theta of s directly back to f of x and y. As you see, we didn't have any Fourier transform operation here. We didn't take the Fourier transform, and we did not take the two-dimensional inverse Fourier transform. That's why people were trying to avoid. That's what people were trying to avoid, trying to take the two-dimensional inverse or forward Fourier transforms, which is very computationally and memory-wise inefficient and difficult for at least old computers. I believe nowadays, maybe they're not even consulting to this formula anymore because they don't need to. Today's computers are probably strong enough to do it. But remember that the CT images are also very large, like at least megapixels, maybe even more. So therefore, they may need to consult formula. Anyway, so what we have discovered from the beginning of this course, from here until the last formula, is the analytical way of determining the computed tomography image. But before that, I told you that we are also going to talk about alternating projections, and this will this is supposed to be also an example of that alternating projections, and that's what we are coming to right now. But I think 1027, it's already about an hour. Let's give a break of about half an hour, and let's start at 11 o'clock and continue with the way to perform this computed tomography using projections, using solving linear set of equations, using alternating projections. And I will also give you a few more examples of alternating projection implementations, as long as the sets that we will describe are convex. What will that mean? We will have to explain. So let's leave for now. You have now the formula of computed tomography in terms of analytical things, and you also know the Redon's transform, which was at the top, and the Redon's inversion formula, which is here. I recommend that you go through Redon transform in other literature to study a little bit more, because in the final examination, I tend to ask the Redon transforms of some certain specific well-known signals. Redon transform is not our discussion topic. I'm not going into the details of that, but I want you to learn it. That's why I tend to ask those Redon transform questions in the final take home. So you will have to make the research to solve those questions anyway. But I will continue in the next hour at 10 o'clock using alternating projections. So right now I'm stopping the recording.